Okay, we may begin. Hi, everybody. So last time we discussed some issues related to kinematics. Today we will repeat the Newton's laws, the laws of classical dynamics, or the Newton's laws of motion. First of all, write down what is written on the blackboard. The first Newton's law: a body at rest remains at rest unless acted on by a net external force. We will discuss it in detail later. A body at rest remains at rest unless acted on by a net external force. And the second law, you can describe this formula using the words, something like the acceleration of a body, the acceleration A, is directly proportional to the net external force acting on the body and inversely proportional to its mass. And the third Newton's law: for every action there is an equal and opposite reaction. That is a short formulation of Newton's laws. I'm sure you heard about it. In every country of the world, every school children knows, if he graduates from school, then he has heard something about Newton's laws. So the first Newton law says that the body at rest remains at rest. How can we understand it? If the body is at rest, it means that it's not moving. It's remaining on its initial position. How can we measure a position of the body? How can we measure a body coordinates? Only using some coordinate frame or some coordinate system. So we must have a coordinate system which is certainly a rigid body and some rod, rigid rod, which allows one to measure distance or coordinates along the x-axis. So coordinates with respect to some rigid body can be measured in this direction, and there is another body, which remains at rest somewhere, if not acted upon by other forces. So in order to understand the first Newton's law, we must keep in mind that there is always some reference frame in relation to which we measure the coordinates of a body under consideration. Because there are no absolute coordinates in space, no absolute motion. Any motion is always considered with respect to some other body, with respect to some system of reference. Any motion is considered only as related to some reference system. So we must measure this coordinate using some reference system, some other body. And if this body under consideration is not acted on by other forces, then it remains at rest. Is it always true? No, not always. It may be true only in case the reference body is also at rest. If the reference body is moving with acceleration, for example, then the body under consideration will also have some motion, some acceleration. So what the first Newton's law says actually means that there is always such a reference system that if we consider some other body related to this reference system, in relation to this reference system, and if no forces act upon this other body, then its coordinates remain at rest if it was at rest. If a body is at rest, then it remains at rest. The reference frame which has this property is called an inertial frame or inertial system, inertial reference frame. So if we have an inertial reference frame, then another body will remain at rest if it was at rest, unless other forces act on it. What if we go to another reference frame, which is moving with respect to the first reference frame at constant velocity? Then the body under consideration will be moving, will have some velocity with respect to the second reference frame. And if the second reference frame moves at constant velocity, then the body under consideration will also have such constant velocity with opposite sign. So the first law may be expanded to include all the inertial reference frames that move with respect to one another at constant velocity. You can say that a body at rest remains at rest, and a body in motion will remain in motion at constant velocity unless acted upon by a net external force. I told you that not every reference frame has this quality. Only inertial frames. If the frame is not inertial, if it's accelerating, then the first Newton's law does not work. And so, if you think about this issue about different inertial reference frames moving with respect to one another, and how the motion of the body under consideration looks from different inertial reference frames. If you think about it, you will understand, you will come to an inevitable conclusion that the first Newton's law states that there is at least one inertial reference frame in the universe, at least one. If there is one inertial reference frame, then there are many other reference frames, inertial reference frames, having the same property. Those frames which move at constant velocity with respect to the initial reference frame. So if there is one inertial reference frame, then any other reference frame moving at constant velocity will also be inertial. So you can reformulate the first Newton's law in the following way. There is at least one inertial reference frame in the universe. That's the statement. It's not obvious. It's not obvious. But the world we live in has this property. There seems to be an inertial reference frame in it. Why? Because the motion of any body under consideration can be considered only with respect to some inertial reference frame. That's because any motion is never absolute, and any coordinate of a body is never an absolute coordinate. Any coordinate is measured with respect to some reference frame. Okay, that's it, the real meaning of the first Newton's law. There is at least one inertial reference frame in the universe. The second Newton's law is well known to all graduates from secondary school. An acceleration of a body is proportional to a net force, directly proportional, and inversely proportional to the mass of this body. What is the net force? The net force is the vector sum of all forces acting on a body. So if you have some object, and if several forces act on it, the force F1, the force F2, etc., many other forces may be present here, then the net force is just the sum, vector sum, F1 plus F2 plus maybe other forces if present. And so we say the net force, meaning the vector sum of all forces. So here we have the net force and the mass of the body. In order to be able to use this law, we must have some instruments to measure the mass, and we have some means to measure forces. If we are unable to measure forces and unable to measure mass, then we are unable to use this formula. How can we measure mass, a mass of the body? By comparing this body with some other reference body or sample which has a unit mass by convention. So people agreed that some sample body has a unit mass, which is called 1 kilogram, for example. And so with this 1 kilogram body, we compare all other bodies, for example, using balances. So by comparison of a given body with a sample body, we can measure the mass of a body by weighing on the balances. And how can we measure a force? There are some instruments to measure the force. For example, if you have a spring, then the spring will elongate if you pull it downward with some force. If I attach a mass here to the spring and leave them alone, then the spring will somewhat vibrate and then it will stop vibrating, but the length of the spring will be larger than the original length. So the elongation of the spring can be taken as the measure of force. So there are some means to measure force, some instruments. There are many instruments, actually. Many different instruments to measure forces. And we will discuss some of them later. So I wanted just to underline that in order to use this formula and in order to calculate the acceleration, you must have some instruments to measure the force and mass. And to measure always means to compare with the unit of measurement. When we measure mass, we compare it with a unit mass of 1 kilogram. When we measure force, we compare it with a unit force which is what? Certainly, you know, its unit of measurement of force is called 1 Newton, which can be calculated from this formula. What is 1 Newton? A unit for measurement of force, which is a unit acceleration times unit mass. So unit mass is 1 kilogram and unit acceleration is meter per second squared, which gives you the unit of measurement of force. One kilogram times meter, 1 meter per second squared. So if you apply a force of 1 Newton to a body of 1 kilogram, then this body will obtain acceleration of 1 meter per second squared. That's the meaning of this unit. And certainly you have heard about the third Newton's law. For every action, there is an equal and opposite reaction. What does it mean? It means that if two objects somehow interact with each other, one object and another object somehow interact. For example, by means of a spring. So the spring, if you compress the spring, it will act with some force on this body and with some force on this body, attempting to push them away. And so the force acting on one body will be equal and oppositely directed to the force acting on another body. So the third Newton's law says that the vector F1 equals minus vector F2. A force of action is always equal and opposite to a force of reaction. Whatever interaction you consider. You may consider interaction of two electric charges, a positive charge and a negative charge. They are attracted, and the forces of attraction will comply with this law. You may consider some gravitational interaction, like forces acting on the moon from the Earth and forces acting on the Earth from the moon. Two forces of gravitational interaction will also comply with this law. One force will be equal to another one with a sign minus. Whatever force you consider. You may exert a force on a wall. So I act with some force on the wall, but I feel that the wall is acting with similar force on me. All of you are aware of a gravitational pull which is acting on you and pulling you downward, but you feel the opposite force from the bench, which supports your body and doesn't allow you to fall down through the surface of the Earth. If it were not for the force of reaction, you would never be seated here. You would fall down through the floor because of gravitational pull. But all of you are at rest on your benches because you feel the force acting on you from the bench and supporting you and balancing the gravitational pull directed downward. And the force from the bench is directed upward. So the two forces balance each other, and for this reason you are here in this audience, in this classroom. So, shortly about the Newton's laws, and in order to solve problems, which is the main purpose, your main purpose is to learn how to solve problems. So we will solve problems most of the time. And while solving problems, especially from this collection of problems by Bukovtsov, you will discover that some forces are measured in this unit. What does it mean? This is called a kilogram force. A kilogram force. And 1 kilogram force, what does it mean? Actually, the force with which the Earth pulls down the mass of 1 kilogram. So if you have a mass of 1 kilogram on some support, the gravitational pull is mg, mass times acceleration of free fall, the mass of this body. If the mass equals 1 kilogram, then the force, this force, is 1 kilogram force. So 1 kilogram force is acceleration of free fall times 1 kilogram. And acceleration of free fall is approximately 9.8 meters per second squared. So 1 kilogram force is 9.8 kilograms by meters per second squared. That is 9.8 newtons. That's what is 1 kilogram force. 9.8 approximately. 9.8 newtons. This approximation is quite acceptable. It's enough for solving most of problems. You don't need to consider many more digits here. Enough to have 2 digits. I just wanted to ask you, have you received my message concerning the home assignment? Who was the first to send me his home assignment, or her home assignment? I don't. Who? You sent me the first one. Oh, you're the first. Yeah, you're the only student who sent me a home assignment. Yes, for the first week. So every week you will have to send me your home assignment for the previous week. Well, I know it's time consuming. I know it takes some hours to solve all the problems, but it's necessary. It's absolutely necessary for you to solve all the problems and to be able to solve any problem from Bukovtsov. Actually, you must be able to solve any problem from this collection of problems in order to be successful at the exams. I mean the written test, final written test, and final oral exam. The main purpose of your studies is not simply to remember formula. It's not the main purpose. Sure, you must know the formulas, but you must be able to apply these formulas to solve different problems. That's the main purpose of your studies, to be able to apply laws of physics and physical formulas in problem solution. So we will continue by solving some problems. And what if we use this instrument? Oh, it's good enough. So the first problem I wanted to consider is number 41 from the Buchovtsov collection of problems. Number 41. It says, 6 forces lying in one plane and forming angles of 60 degrees relative to one another are applied to the center of a homogeneous sphere with a given mass. The mass is given. These forces are consecutively equal to 1, 2, 3, 4, 5, and 6 kilogram forces. In what direction and with what acceleration will the sphere move? So we have to find the direction and magnitude of acceleration. So we have to find the vector A, both magnitude and direction. So what does it say? What does it say about the forces? There are 6 forces. So there is a sphere and 6 forces acting at angles 60 degrees relative to one another. So this is force number 1, which is 1 kilogram force. At 60 degrees, force number 2, which is 2 kilogram forces, and then at 60 degrees, force number 3, force equal to 3 kilogram forces, and in this direction we have force equal to 4 kilogram forces, and in this direction even larger force, which is 5 kilogram forces, and in this direction the maximum force, which is 6 kilogram forces. And all these angles are equal to 60 degrees. And the mass of the sphere is given. And we have to find the direction and magnitude of acceleration of the sphere if 6 forces act on it. So we have to find, first step, we have to find the net force. In order to use this equation of the second Newton's law, we have to find the net force acting on the body. The net force is the vector sum of all forces. So we have to calculate somehow the vector sum of these given vectors. The easiest way to do it in this particular case is to consider forces acting in one direction along one straight line. We have the force directed upward and equal to 1, and the force directed downward and equal to 4. So the net force, if we add this vector and this vector, what we will obtain? We will obtain a net force acting in this direction and equal to 3. 4 minus 1. The force equal to 4 is acting downward, and force equal to 1 is acting upward. So that when we add these two vectors, we must actually subtract these numbers. 4 minus 1. The force equal to 3 kilogram forces directed downward. The same consideration for another direction will give us 5 minus 2. Another force equal to 3 directed along this line. And the last line, 6 kilogram forces minus 3, will give us another force again equal to 3 kilogram forces. So after combining 6 forces by pairs, we obtain 3 resultant forces. These 3 forces act in the same way as the 6 original forces. So instead of the 6 original forces, 1, 2, 3, 4, 5, 6, we consider only 3 forces which we have just obtained. So now we forget about the original forces. We forget about this one and this one and this and this and this and this. We forget about it. We have already taken them into account. And now what we have, only 3 forces acting at angles 60 degrees to one another. So on my drawing, these 2 angles are not quite equal, but they should be equal. So I will try to reproduce this picture here, and I will try to show the equal angles, this one and this one and this one, so that these 2 angles are equal. And each vector in magnitude equals 3 kilogram forces. We have to find the vector sum of these 3 vectors. How can we do it? All the vectors are of the same magnitude, but different direction. Consider the action of all the vectors along this line and along perpendicular line. If we add this vector and this vector together as symmetric, 2 symmetric vectors with respect to this direction, 2 vectors located symmetrically with respect to this line, if we add them together, we must draw a parallelogram which will produce the result. The result of the summation of these 2 vectors will be the diagonal of this parallelogram. So the diagonal will be equal to 3 and another vector equal to 3. So the sum of these 2 vectors will be 6 kilogram forces. You can put it in a slightly different way. You can say that if we consider a projection of this vector and this vector, 2 projections on this direction, so this may be x axis and this is y axis. So we consider the projection of vector 3 on axis x and y. This is the projection. This is the component of the vector on the y-axis, and this is again the component of the same vector of the same magnitude on the y-axis. So these 2 angles are equal. This is 30 degrees, and this is also 30 degrees. So the components of this vector along the y-axis are equal and oppositely directed. So they will cancel each other. They will balance. And what will remain here, only the component of each vector directed along x-axis. So the first vector will have component equal to half the diagonal, and the second vector will have the component along the x-axis equal to half the diagonal. And so the two components will give the whole diagonal, which is 3 kilogram forces, and the remaining vector looking in the same direction. So 3 plus 3 will be 6. 6 kilogram forces is the magnitude of the net force acting on the sphere. And where does it look? This net force looks at the direction of vector, original vector, equal to 5 kilogram forces. Originally we had six vectors initially. 1, 2, 3, 4, 5, 6. There were 6 vectors, and the net force is directed, has the same direction as the original force number 5. So this is the direction of the force, and this is the magnitude of the force. So we have found both magnitude and direction. So we have answered the question of this. We have found the answer to this problem. We have found the direction and magnitude of acceleration, because acceleration is defined, the vector of acceleration is defined by the vector of force. Mass is given, not a problem. It's not a problem to divide 6 by what we have. Mass is 4 kilograms, if I'm not mistaken. So it's not a problem to divide 6 kilogram forces by 4. Let's do it. Let's do it. Anyway. So I omit the sign of vector here because we have already found the direction, and we don't have to talk about the direction. We have established it. So we're now talking about the magnitude of acceleration. The magnitude will be the magnitude of vector F, which is 6 kilogram forces over the mass m, 4 kilograms. And what is, so we have 6 over 4. And what is 1 kilogram force? I told you this is 9.8 kilograms times meter by second squared. So if we consider this 9.8 approximately to be approximately 10, that's okay. That's enough for many problems. 9.8 is approximately equal to 10. 6 over 4 is 1.5 times 10. That will be 15 meters per second squared, because kilograms cancel here. So the final answer is, we have to find acceleration. Okay, we found it. Acceleration will be 15 meters per second squared. And the direction of this acceleration will coincide with the direction of force number 5. That's it. That problem was devoted to the issue of net force. What is the net force and how to use it? We have calculated the net force as the vector sum of all forces acting on the body. And the next problem that we will consider is problem number 53. Number 53 from Buchovtsev. A weight G is attached to the axis of a moving pulley. So there is a sketch of what's going on. So there is a string that goes around the moving pulley, and the weight is attached here. This is the weight G, and the string goes through the fixed pulley, and then it's pulled by force F. So a weight G is attached to the axis of a moving pulley. What force F should be applied to the end of the string? In the problem it says the rope. I don't like the word rope. Rope is something, well, you can use it, it's not a mistake, but I prefer to use the word string or thread, something like that. So we have to find force F in this problem. What force F should be applied to the end of the rope? It says passed around the second pulley so that the weight G moves upward with an acceleration A. So acceleration A is also given. We have to obtain such acceleration. And what force should be applied? Another question. What force F should be applied so that the weight G is at rest? Disregard the mass of the pulleys and the rope, and I would add disregard friction in pulleys. So both pulleys have no mass, and the rope or string has no mass. The mass of the string is negligible, and the mass of each pulley is negligible, and there is no friction here in the axis of the pulley. So the situation is ideal. We must take into account only forces acting on this body, and we have to calculate this force disregarding all other forces and masses. Okay, so if this string is pulled down with a force F, then this will be the force of tension, the force of tension in the string. And this force will be the same here. The same force will be here, the force of tension. And the same force will be here. Why? Because there is no friction, and because the mass of the pulley is negligible and the mass of the rope is negligible. And what is discussed here is that if you have just a string and you pull it down with force F, so this will be the force of tension in any point of the string. This is a string, and in any point you may break the string here and insert a small spring to measure the force of tension. And elongation of the spring will show you what is the magnitude of the force pulling the spring. And you can measure force here, and you can measure force in any point of the string. And everywhere the force will be equal to F, here, here, and here. Why? Because the string has very small mass. The mass is zero. The mass is neglected. We neglect the mass of the string. That is why the tension inside the string is the same in every point of the string. The same situation is here, with the only difference that the string passes around the pulley, but this makes no difference because the pulley itself has zero mass and there is no friction here. So these forces are the same, the force of tension here and the force of tension here, the same. In order to find the acceleration of this body, suppose the acceleration is directed upward, we have to apply the second Newton's law. And in order to apply the second Newton's law, we have to consider all the forces acting on this body. To find all the forces we must remember that a force is a measure of interaction. If you have an interaction between two bodies, there is a force. If there is no interaction, then there is no force. So a force is always a measure of interaction. In order to find all the forces acting on this body, we have to consider all the interactions of this body with the outside world. There are only two outside objects with which this body interacts. First, the string, this one, and second, the earth, which pulls this body downward with the force equal to the weight of this body. And the weight is given, the weight is g. So this is the weight of the body, which is always the mass of this body times acceleration of free fall. So this is the gravitational pull of this body applied to this body and directed downward. Why? Because any object is interacting with the planet Earth, and the planet pulls this body downward. So only two objects in the outside world with which this body interacts. There are only two objects, the Earth and the string. The Earth pulls down the object with this force, and the string pulls up with some other force. We have to invent a character to designate this vector. So let it be T, force T. You can choose any other letter to designate it, to denote this force. So now, as we have considered all the forces and we know all the forces and the mass, if we know the forces and the mass, we can write down the second Newton's law, which is what? The mass of the body times acceleration must be equal the net force acting on the body. The net force is what? If we have chosen the positive direction upward, then downward will be the negative direction. And then all the vectors directed upward will be positive, and all the vectors directed downward will be negative. And so in this equation, vector t directed upward will be positive, and g directed downward will be negative. That's it. The second Newton's law applied to this object. Mass times acceleration is equal to the net external force. Is this equation enough to find acceleration? No, because we have only one equation and two unknown quantities. Mass is known, the weight of this body is known, but we don't know acceleration, and we don't know this force T, the tension in this string. Two unknown quantities in one equation. It's impossible to find anything. We must somehow write down another equation in order to solve the problem. Two unknown quantities for one equation is too much to solve it. So another thing we may consider is the motion of this pulley. Yes, it has zero mass. The mass of this pulley is zero. But anyway, even with zero mass, what is zero mass? I told you it's an approximation. Actually, there is some very small mass, but we neglect it. Anyway, the mass is, it's not a good thing to denote the masses of these two bodies using the same letter. So let it be m0, the mass of this pulley. It's very small. It's very small. Anyway, it is there. Even it's 1,000 times smaller than m, m0 may be 1,000,000 times smaller than m. No problem. Anyway, there is some mass. So if there is some very small mass, we can apply Newton's law to this pulley. How to do it? Again, the mass of this pulley, m0, which is very close to 0, times acceleration, and note that the acceleration of the center of this pulley and this body will be the same because they are connected by a non-stretchable string. Non-stretchable string. So the distance, if the string is non-stretchable, then the distance between these 2 points will remain the same. And so the velocity is the same and the acceleration of these two bodies will be the same. So the acceleration of the mass m0 will be the same, a. I don't have to use a different character here, the same character a, because the acceleration is the same. And now the forces, the net force acting on this body. Two forces F acting upward and one force T acting downward, because the string, which is here, pulls down the pulley, minus T. And we know that m is very close to 0. So all this is 0, and this should be also 0 in our approximation. Approximation consists in neglecting the mass of the pulley. So if the mass of the pulley is 0, then this combination of forces must be 0. So we have two equations. And combining these two equations, it's possible to solve the problem. How to combine these two equations? We may add the two equations. We may add them. ma plus 0 will be ma equal to t minus g, and plus this expression 2f minus t. I just added the second equation to the first equation. This is 0. So ma plus 0 must be this expression plus this expression. T minus g plus 2f minus t. Okay, t cancels here. And what we have to find? We have to find the force F needed to arrange for the body to accelerate with acceleration a, to move with acceleration a. We have to find the force F. Okay? Is it difficult to express the force F here? No. So that will be ma from this equation plus g divided by 2. What is g? G is known. G is mass of the body times acceleration of free fall. Instead of g, I write here mass times acceleration of free fall divided by 2. So what we have here is mass over 2 a plus g. That may be considered to be a final answer. Mass, you may consider the mass given because g is mg. So if g is given, then you may consider mass to be given. Mass is not a problem. You know the mass, and acceleration a is given, and acceleration of free fall is given. So this formula includes only quantities known to you. Every quantity is known. in this formula. And so we have calculated force F. There is another question in this problem. What should be the force F for the weight G to be at rest? What does it mean that the body G is at rest? It means that its acceleration is 0. Instead of A, it's 0. So in order to find the answer to the second question, we must use the 0 acceleration here. And so we immediately obtain the answer to the second question, F2, the force which we need to apply here to the string, now F2, in case the body G is not moving. It has 0 acceleration. If acceleration is 0, I just substitute 0 for A here and obtain mg over 2. What is mg? This is the weight of the body, denoted by capital G. So you have to pull this string by force F2 equals just half the weight of the body, of this body, in order to keep this body at rest, so that it doesn't move. It has no acceleration, neither upward nor downward. You have to apply here to the string the force F2 equal to half the weight of the object, of this body. Any questions? Yeah. Oh, too small, too small. Can you increase the font? Yeah, it's better. Now, concerning the sound, somebody has no sound. I mean the guys who are at distant learning. Someone has no sound, okay. Another question is concerning the home assignment. Yes, before October 18th. October 18th, the nearest Sunday, is the last day for sending the home assignment of week number 2. All the problems under the week number 2 assignment, week number 1, I'm sorry, week number 1 assignment should be sent before or on October 18th. Well, you understand that the next Sunday, the nearest Sunday, on October 18th, you will have to send so October 18th, week number 1, all problems under the schedule for week number 1. The next Sunday after this one, October 25th, you will send all the problems under the week number 2 schedule, and so forth and so on. Each consecutive Sunday, you send another week, the next week, problems. Such was the question. And then, what else? Well, somebody made a mistake. Not a problem. Not a problem. It's not correct. It's a mistake. Well, as far as mistakes are concerned, don't be afraid of mistakes in your solutions. I tell you, who makes no mistakes at all? Who? Do you know? Who makes no mistakes? Who does nothing? If you do nothing, then you do no mistakes. You make no mistakes. If you do anything, you will make mistakes, inevitably, because any human being makes mistakes. It's not a problem. It's not bad. It's not bad to have a mistake in your solution. Well, it's very bad not to solve the problems, but it's not bad to have a mistake. On mistakes, on your mistakes, you learn how to solve. Well, I will show you mistakes, your mistakes, and you will learn how to solve, how to avoid mistakes. So don't be afraid of mistakes. They are inevitable. Everybody makes mistakes. And the most important thing is to be able to find your mistake and correct it. That's the most important thing in your studies. Yes? Sorry? I will look at all your solutions, and if I find it necessary to attract your attention, to draw your attention to some of your mistakes, I will answer you. But if your solution is absolutely correct, or if there are just minor mistakes, like arithmetic mistakes, I will not pay attention to this. It's not very important. So every week you send me your solutions every week, and then finally I will communicate with each one of you and ask you some questions concerning your solutions, and you will have to send me your answers, your explanations and clarifications, how you understand your own solution, how can you explain it, and that if I find your explanations good, then that will be the end of defending your homework, home assignment. Yes, you have a question? Yes, it's not very important. I will make mistakes. When I deliver lectures during the whole semester, I will make 2 or 3 mistakes. And if you find it, immediately show to me where I have mistaken, where I did it. So everybody makes mistakes. It's not a big problem. It's not a big problem. I will tell you, if your mistake is principal, for example, well, the mistakes are different. If instead of using this law of mechanics, you try to use some other law, this is a gross mistake. I will certainly tell you that you are using the wrong law. But if you use correct law and make all correct calculations, and somewhere you have just missed some letter, well, this is a minor mistake. If all the solution is correct, but somewhere you missed it, it's a minor mistake. It's not a problem. Well, I wanted to discuss some other situations related to the second Newton's law. I wanted to discuss an object on the slope. So we have an inclined surface, a slope, and a body, a block on the slope. The block can move along the slope. And how to apply, it's very important to understand how to apply the second Newton's law in this situation. Suppose we know the mass of this body, and we want to calculate the acceleration. We want to calculate the acceleration of the body. What is the correct way of reasoning? First, in order to find acceleration, we have to find what? Net force. This one. Net force. What is the net force acting on the object? This is the vector sum of all forces acting on this body from other external bodies. In order to find all the forces, we have to consider all the interactions of this body with the external world. We have to find every other object with which this body interacts. What are the interactions here? What interactions are involved in this situation? First, this body is attracted by the Earth. This is the gravity pull mg, directed downward, vertically downward, to the center of the Earth. And there is another body with which this block interacts. That is the slope, the surface of the slope. First, we consider the simple situation without any forces of friction. So if we have no forces of friction which are directed along the surface, then the force of interaction with the surface will be perpendicular to the surface. And we denote it by letter N. This is the force of interaction of this block with the surface of the slope. Why this force N is perpendicular? In general case, it's not perpendicular. In general case, this force of interaction may be directed at some arbitrary angle if we have friction. But if there is no friction, then no force is acting along the surface. And so all the forces of interaction with the surface may be directed only perpendicularly. So in this problem we have two directions which are of interest. The direction parallel to the surface, let it be axis x, and the direction perpendicular to the surface, let it be axis y. What is obvious in this problem, in this situation? It's obvious that the block cannot move through the surface downward. And it's obvious that this block cannot jump into the air and separate from the surface. It's obvious that the block can move only along the surface. And its velocity and its acceleration may be directed only parallel to the surface, that is, parallel to x-axis. It means that all the velocities and accelerations along the perpendicular y-axis should be zero. This body is unable to jump off, and it cannot go through the surface. That's why all the acceleration, the vector of acceleration, can be directed only along x-axis, and along y-axis acceleration is zero. So we can write that the component of acceleration along y-axis is zero, because this block is unable to jump into the air and separate from the surface. That is obvious. It's just a brick. It's just a brick. It's unable to jump. So if acceleration in perpendicular direction is zero, then from the second Newton's law, we see that the net force acting along the perpendicular direction, along the y-axis, the net force is also 0. The net force acting along the y-axis. So we know beforehand, we know immediately that all the forces acting along y-axis added together shall give 0, shall balance, shall cancel each other. In order to find the forces acting along this perpendicular direction, we must find the component of the body weight on the y-axis and another component along the x-axis. Let's denote this vector as r and this vector whatever you like, t. So if there is no acceleration along y-axis, if acceleration is 0, then 0 shall be the vector sum of all vectors directed along y-axis. And we have only two vectors here, n directed upward and t directed downward in the opposite direction. From here, we immediately obtain, I will put such a symbol, an arrow, which means the consequence. What is the consequence from here? The consequence is that n equals t. Magnitude, the magnitude of n, vector n, equals the magnitude of vector t. And the magnitude of vector t can easily be obtained from geometrical considerations. If we know this angle is alpha, then this angle is also alpha, and t shall be mg cosine alpha. This is from geometrical considerations, from this triangle. The adjacent leg in the right triangle can be expressed in this way, using cosine function. So if we know t, then we know the magnitude of n. This is mg cosine alpha. We obtained the force of interaction between the block and the surface. We found this force using the mass of the body, the acceleration of free fall, and this angle of inclination of the surface. How did we find it? We found it from the very simple observation that the block is unable to jump from the surface, and it cannot break through the surface if the surface is solid, if it's rigid, if it's not made of thin paper. So the block cannot go through the surface and it cannot go up away from the surface. Only from this consideration, only from this observation, we found the magnitude of the force of interaction between the block and the surface. Certainly using the second Newton's law. And now, if we consider this right triangle, then alpha is here, and the force R can easily be calculated from the geometrical considerations as mg. Mg is this magnitude, the length of this section, times sine alpha. I hope you remember all these formulas from geometry. If you have a right triangle with the sides A, B, C, and this angle is alpha, then B divided by C by definition is cosine alpha, and A adjacent leg divided by C. Sorry, the first mistake. 3 for the semester on average. This is B over C is sine alpha, and here is cosine alpha. The adjacent leg gives you cosine, and the quotient of the of this leg to side C, and this is the right angle. And also it's useful to know that B over A is tangent alpha. This is just the definition. This is not a big science. This is just a definition. What is the sine of angle alpha? What is the sine? Nothing more but the result of dividing the length of this section to the length of this side. Nothing more. What is cosine? Just by definition, A divided by C. You must know a lot of definitions of different mathematical quantities and physical quantities. You must know what is the velocity, what is the acceleration, what is the force, what is the sine or cosine of angle, etc., etc. A lot of definitions. Write down all the definitions in your notebook, thick notebook for theoretical studies. Write down and repeat them regularly. You will be unable to remember them without regular repetition. Repeat them every week at least. Repeat all the definitions and repeat all the formulations of physics laws. There are many laws. In the course of physics, you will encounter dozens of physics laws, and in order to remember all of them, you will have to repeat them regularly. So all the laws and all the definitions must be written in your notebook. And you must open the notebook very often, at least once a week or twice a week, and repeat the major definitions, the most important formulas. So, if you want to find the acceleration of this mass, the acceleration directed here, we have to use the Newton's second law. We have to find the net force acting along the x direction, and this is r, the net force, and divided by the mass of the block. And the net force is equal to mg sine alpha over m. So the acceleration will be g sine alpha. The acceleration of the block on the inclined surface, on the slope. If there is no friction. Now suppose there is some coefficient of friction. Suppose there is some coefficient of friction here on this surface, and the coefficient of friction is given. Then there should be a force of friction acting on the block and directed against the velocity, in opposite direction to the velocity. So this will be the force of friction. And the force of friction is always equal to coefficient of friction times normal force, N. Why so? Because this is the definition of coefficient of friction. This is not the physics law. This is the definition of K, friction coefficient. By definition, K is chosen to be such that the force of friction is given by this formula. It means that by definition, coefficient of friction is the ratio of the force of friction divided by N, by the force of by the normal force of interaction of the block with the surface. So this is the definition of the force of friction. And now, if we want to calculate the acceleration of this block, from the Newton's second law, we will obtain that the acceleration, mass times acceleration, let it be so, equals the net force acting on the body along the x-axis. And if the positive direction of all the vectors is chosen to be here, downward along the surface of the slope, then all the vectors directed in this direction will be positive, and the force of friction will be negative. So the net force acting along the x-axis, that is along the x-axis, the net force will be R minus force of friction. Yes, we know what is R. We may substitute for R this expression, mg sine alpha minus F force of friction. And we know what is force of friction, Kn. K, and we will substitute for N this expression. This expression will be substituted for N. So coefficient of friction times N, and instead of N, I write down mg cosine alpha. So I need to calculate acceleration. In order to calculate acceleration, I have to divide by m. Dividing by m, I will find it that the acceleration now is g sine alpha minus k cosine alpha. That's the acceleration of the body directed downward. We just divided by m this equation. And where did we get this equation from? From the Newton's second law. Mass times acceleration is the net external force. And the net external force is calculated like this. So we can divide all this equation by m, and we obtain what is written here. That will be the acceleration of the block directed downward. Now look, suppose the angle alpha is very small. If it's very small, then the sine will be very small, close to 0. And cosine will be close to unity. So if the angle alpha goes to 0, it's very small, then the first term here will be very small, it goes to 0. And the second term will tend to k, because cosine will tend to unit. And we will obtain that acceleration equals minus k for very small angles. Very small angles is almost horizontal surface. So if we go to horizontal surface, the surface of the table, and I put here any object, it must move immediately with some negative acceleration. Absurd result. Why? Why we obtain the absurd result? Who knows? If angle alpha, I repeat, is very small, small angle means that the surface is almost horizontal, then this formula will give you 0 for the first term and k for the second term, because cosine of very small angle is equal to 1. So the acceleration will be equal to minus k, and k is coefficient of friction. It's a finite number, like 0.3, maybe 0.5. Oh, sorry. There is certainly g is here and g is here, so that should be taken in round brackets. So acceleration will be minus kg if the surface, the inclined surface is almost horizontal. But we don't observe such acceleration of any object put on the horizontal surface. Nothing is accelerating. Everything is standing still on the surface. It's not accelerating. But the formula gives you acceleration. What's the matter? Who knows? Well, this is the end of our lecture, and I can just give you a hint. The formula is absolutely correct, but physical interpretation of this formula is very subtle. If you apply correct interpretation, you will never get an absurd result. Like anything put on the table must be immediately accelerated in some direction. This is an absurd result. We never observe such things that anything on the surface of the table is immediately accelerating somewhere. No, never happens. That never happens. But the formula itself gives you this result. I give you a hint. The formula is correct, but the interpretation needs a little bit thinking. You need to work over this problem, okay? Think about it at home. And now we have the end of this lecture. Thank you. Mm-hmm.